The purpose of this lecture is going to be to talk about electrical resistance. Now, we've talked about conductors, we've talked about insulators, we said that conductors allow charges to flow. And we like to just think of wires as being, hey, we've got electrons we want over here to flow, we want them to go over here, just hook them up with a wire, forget about it. The problem is, we have to remember that these are made up of atoms and molecules, and how electrons interact with those maybe isn't as simple as we think. It turns out that almost all materials, with one exception, are a category called superconductors. They don't transmit all of the energy that you put in per charge. Some of that energy is lost in other forms, such as heat. So why is that? Well, I've got a wire here, and let's say I hook my wire up to a battery. Now I've drawn the crystal structure of the copper here. So to remind us that it's made up of atoms. So I think it's pretty clear what's going to happen. Electrons are going to flow out of the negative. They're going to flow into the positive. So there's going to be a pressure for electrons to be going this way through the wire. We'd like to say that that's like a river. They go in just one direction. But it's not really true. What's actually happening is they are going all around. And there's a very small drift speed that means over time, they actually do make it from one side to the other. But all of this moving around, it knocks the copper atoms around, it gives them kinetic energy. And the kinetic energy of atoms is actually what temperature is. So what's happening here is this wire is converting some of the electrical energy that I wanted to go through it. It's converting it to heat.
So basically, there must be some property that describes how much an electrical device slows down the flow of charge. And that property is called resistance. Resistance is the ability of an electronic device to impede the flow of charge. So we could do a number of experiments in class to determine what contributes to resistance. One of the ones I like to start with is with this vintage demonstrator that I found on eBay. It basically consists of 5 coils of wire. There's 10 meters of relatively thick copper, and there's 20 meters of that same wire. There's 10 of thin copper and 20 of that same wire. And then there's 10 meters of the exact same diameter and length as the first coil, but made of a different material, nickel silver. And basically, by comparing how the resistance of these wires changes as their properties change, we can start to figure out what might contribute to the resistance of an object. So for determining the effect of length on resistance, I think coils 1 and coil 3 would be useful to compare. Also coil 2 and coil 4. So here are those results, and we can see 3 has more resistance than 1 and 4 has more resistance than 2. So together that suggests that resistance may be proportional to length. Note that we don't really conclusively show this. We had 2 data points, but at least from our 2 data points, which we verified with another 2 data points, it appears that there's some sort of positive correlation. So this is kind of suggesting a pattern to us, but not conclusively showing it. So we could play the same game. We can compare coils 3 and 4, which have the same length but different cross-sectional areas. Same with coils 1 and 2. Let's see what those results look like. So in either case, the thicker coil had much less resistance than the thinner coil. So that suggests that cross-sectional area, having more of it, may lower your resistance. So I've suggested an inverse proportionality here. Again, we would need more data points to verify that. So the last comparison to make is between the final wire, which is nickel silver, and the first wire, which is copper. And other than that, they have the same dimensions. Let's see what the resistances look like. So if we compare coil 1's resistance to coil 5's, we see that the nickel-silver wire coil 5 has much more resistance than the copper coil 1. So that suggests that what material you're made of has something to do with your resistance as well. Let's try to put all of these ideas together into some sort of coherent equation.
So the things that contribute to resistance, which we give a capital R, the longer the wire is, we expect that to increase resistance. So I'll put an L there for the length of wire. The fatter the wire is, you'd expect to decrease resistance because it wouldn't have to be all trying to go through a few atoms. There'd be more atoms for it to go through. So we expect that the fatter we make the wire, the more area, would decrease resistance. And then lastly, what type of atom is it? We expect each material is going to behave slightly differently. So there's a factor we call resistivity. It gets the Greek letter rho. And that's just dependent on what material you've got. These three things together contribute how much resistance something has.
So I want to be absolutely clear. We have not proven this equation. We have two data points to show the effect of each of these variables on resistance. But our data does suggest this could be true, and it is the actual equation. The first thing I have students do in class with this is play with it and actually end up measuring the resistivity of a pencil lead using Ohm's law in that equation. But we do actually have a device called a slide wire rheostat, which was specifically made for adjusting the resistance and varying it by altering the length of the conductor that current is flowing through. So we could do some experiments with this to at least check the effect of length on resistance in a quantitative way. And what a slide wire rheostat is a big coil of wire, and it's wrapped around this drum. And then there's this thing here that can slide on it, which is called the wiper. So it can just kind of go up and down. There's three places you can hook electricity up to flow through. You could hook electricity up here and here, in which case it might go through the entire coil of wire. But you could also hook it up between here and here. The connection for that is this right here, because this is hooked up through metal. And the reason you would do that is because it makes a connection with the coil of wire there, the path of electricity through would be here, around the coil, and then up through this and out. And by sliding this, that means I can actually change the length of the wire that stuff has to go through. So I'm going to build this circuit here. I'm going to put 25 volts across this rheostat. I'm not going to hook up this end at all. I'm leaving it bare. And I'm going to hook the wiper up to the negative of the power supply, and I'm going to hook the positive up to this end of the coil. I want to put some meters in there too. I've got my voltmeter and my ammeter. So let's remember how they have to go. The voltmeter goes across the circuit. And the ammeter actually has to go in the circuit. So that when I put it together, the electricity is going to flow through part of the rheostat, out the wiper, through the ammeter, and back home. So that'll be the current. All right, let's start putting that together. Hook that up here. And as you can see, we instantly got a current. It looks like it is about 0.2 amps. Now we need to put the voltmeter across. And as we can see, we end up with 25 volts. Let's watch what happens to current. It's like the closer I get it over there, the more the current goes up. And the more I bring it back in this direction, the current drops. And when I have the slider over here, that means electricity has to pass all around this hundreds and hundreds and hundreds of times before it gets to go back to the power supply. And apparently that's slowing down the current. But if I shorten the length of wire, apparently that speeds the current up. So what we can do to check the effect of length on resistance is we can measure the current that passes through the rheostat when there's not much length it has to go through. And then we can measure the current at various lengths as we move down the rheostat. Now we have to be careful. It's not how far we slide. It's the total distance of all the turns, basically. So here's the graph of length versus resistance, and we can see it's very linear. So I think this is much more solid evidence that at least one of our variables in the equation, L, is directly proportional to resistance. The slope of this is interesting. It actually contains information about both the resistivity and area, and in some classes we'll use this slope to figure out what the resistivity of the wire on that rheostat was. I hope after this video you feel a little more comfortable about what the things in this equation mean, and that you feel fairly convinced that resistance is directly proportional to length. I think there's also pretty strong evidence here that the material used matters, comparing that copper to that nickel-silver wire. The last experiment we would need to do is we would need to have wires of different cross-sectional areas but the same length, and we'd have to measure the resistance of lots of those, and I currently don't have a lab to do that. We'll carry out some of these experiments in some classes. Hopefully everybody, though, has a good sense for how this equation is useful.